We're going to move on to discussing fiber optic cabling types. This is just a general summary. Fiber optic media can support higher bandwidths over longer distances than copper wire. The advantages make it a popular choice for long-distance telecommunication networks and for reliable, high-speed networking within data centers. Understanding the characteristics of fiber optic media will help you to understand, support, and troubleshoot existing installations as well as provide upgrades. Fiber optic cable considerations. The electrical signals carried over copper wire are subject to interference and to attenuation. Fiber optic signaling uses pulses of infrared light, which are not susceptible to interference, cannot easily be intercepted, and suffer less from attenuation. Consequently, fiber optic cabling supports higher bandwidth over longer cable runs that can be measured in kilometers rather than meters. That's right, kilometers. A single optic fiber is constructed from 3 elements. Core provides transmission path for light signals, waveguide, otherwise known as. Cladding reflects signals back into the waveguide as efficiently as possible, so that the light signal travels along the waveguide by multiple internal reflections. The core and the cladding can be made from a glass or plastic. The cladding is applied as a thin layer surrounding the core, while made of the same material. The cladding has a different refractive index to the core. The effect of this is to create a boundary that causes the light to bounce back into the core, facilitating the process of total internal reflection that guides the light signal through the core. The buffer is a protective plastic coating. It may be of tight or loose configuration with a loose format using some form of lubricant between the strand and the sheath. In basic operations, each fiber optic strand can only transit light in a single direction at a time. Therefore, multiple fibers are often bundled within a cable to allow simultaneous transmission and reception of signals or to provide links for multiple applications. There are many different outer jackets designs and materials suited for different installations: indoor plenum, outdoor, underground, undersea, so on and so forth. Kevlar strands and sometimes fiberglass rods, strength members, are often used to protect the fibers from excess bending or kinking when pulling the cable to install it. For exposed outdoor applications, the steel shield armor may be added to deter rodents from gnawing the cable. Just give me 1 second, guys. I'm gonna blow my nose real fast. Yeah, allergies are killing me. Okay, guys. Here we go. Single mode fiber and multi-mode fiber. Fiber optic cables are specified using the mode composition glass plastic and core cladding size. For example, 8.3 micron core and 125 micro cladding single mode glass, or 62.5 micron core and 125 micro cladding multi-mode plastic fiber optic cables fall into 2 broad categories. And of course, you can see here the microns and the difference in the wavelengths that it carries. Then we have single fiber, mode fiber, has a small core, 8 to 10 microns, as you can see here, has a wavelength of 1310 to 150. And then laser optics, it's usually used for OS1 indoor or OS2 outdoor, long distance and short range data center applications. And then we have multi-mode fiber, 50 and 62.5 micron core, like we just discussed, 850 to 1300 nano wavelength, optical mode categories, OM1-2 support, and OM2 support using 1 gigabit LED transmitters or 10 gigabit over a shorter range. OM3 and OM4 laser optimized, also known as LOMMF mostly short-range applications inside data centers. We'll move on to fiber optic connector types. As you can see here, the three different types. There should be a fourth. I don't have the fourth. Okay. Fiber optic connectors are available in many different form factors. Some types are more popular for multi-mode and some for single mode. Straight tip, ST, is an early bayonet style connector that pushes and twists locking mechanism. And that's going to be this guy up on top. ST was mostly used for multimodal networks, but is not widely used for Ethernet installations anymore. Subscriber connector. The subscriber connector is a push-pull design allowing for simple insertion and removal. It can be used for single or multi-mode. It is commonly used for gigabit Ethernet. That's going to be this guy right here. And I believe those are most of the time the standard that you'll see. If you go to the Albuquerque campus, you'll see this in our CNST hall up above the hallway at the end. LC local connector is a small form factor connector with a tabbed push-pull design. The LC is similar to the SC, the subscribed connector, but a smaller size allows for higher port density. LC is widely adopted form factor for gigabit Ethernet and 1040. That's going to be this guy down here. And as you can see, there's the tab up there that you can use to depress and remove it from the switch. And then we have mechanical transfer jack, MTRJ. It's a small form factor connector with snap-in design used for multi-mode networks. Yeah, I knew there was four. They only have three images there. Okay. I had to find you guys images for others. Fiber Ethernet standards. Ethernet standards over fiber optics set out to use different types of cable for 100 megabits, gigabit, 10 gigabit, and of course 40 gigabit operation. These are variants for long wave optics required for long distance transmission and short wave length optics. You guys don't have the chart there. I'm going to go ahead and get you a copy of this chart. I'll upload it into chat. That way you can take a look at it while we discuss it. And basically we're looking at what the slide shows here. 100 base, optics, 1300 nanometers, cable, MMF, OM1, OM2, and you can go up to 2 kilometers with this, 1.2 miles. 100 base SX, 850 nanometers, still dealing with the same MMF, but you're only dealing with 550 meters, 1,800 feet. Gigabit SX, base SX, OM1, OM2, and OM3. And that's when you start experiencing the differences here. 902, 550 meters, which usually brings it out to 1,800 meters. And this is a general chart that you'll be able to refer to when you're going to start running cable like this. In most situations, you won't run fiber, but as we progress through time, fiber optics becoming more common. I used to not see many shops do fiber optic in store, and now we're starting to do them in store because we're able to get the splicers that easily. Fiber optic is often used for the backbone cabling in office networks and for workstations with higher bandwidth requirements such as video editing. The principal applications of 10 gigabit Ethernet are better are increasing bandwidth for server interconnections and network backbones, especially in data centers for storage networks. Storage area networks are also known as SAN. Replacing existing switch public data networks based on proprietary technology with simpler Ethernet switches, Metro Ethernet. On to the next slide. Fiber optic cable installation. Fiber optic cable can be installed in the same topology as copper cable using distribution frames and switches. Long distance cables are typically laid out as trunks or rings, with repeaters or amplifiers between cable segments to strengthen the signal. Normally, strands are installed in pairs, duplex. Remember, when you're doing anything in pairs, it's duplexed. Each device with one strand for transmit, TX, and one strand for receive, RX. That's what Caleb was asking about. Why is it one of them say BiX and the other one say TX, RX? Transmit and receive. Fiber optic patch cords for fiber optic can come with the same connector on each end, LC-LC for instance, or a mix of connectors, LC-SC. Duplex patch cords must maintain the correct polarity so that the transport port on the transmitter is linked to the receiving port on the receiver, and vice versa. The TIA EIA cabling standard sets out A to B patch cord to port orientations. Each element in the link must perform a crossover, and there must be an odd number of elements, such as 2 patch cords and a permanent link, 3 elements. You guys see the diagram here. When you see your RX, your TX, and how they're supposed to interconnect. And as you can see, as it states there, you have your receiver and your transceiver. But when you're patching through, you have to have one speak to the other. Most connectors are key to prevent incorrect insertion, so they'll always be labeled, hopefully. But if in doubt, an optical power meter can be used to determine whether the optical signal is being received from a particular fiber. And that's kind of like using a voltmeter to be able to determine if there's a positive charge coming out of a power jack on a laptop or anything coming out of a circuit or transistor. Finishing time. The core of a fiber optic cable is a ceramic or plastic ferrule that holds the glass strand and ensures continuous reception of the light signals. The tip of the ferrule can be finished in one of the 3 formats. Physical contact, PC. The faces of the connector and the fiber tip are polished so that they curve slightly and fit together better, reducing return loss interference caused by light refracting back down the fiber. UPC, ultra physical contact. This means the cable and the connector are polished to a higher standard than with PC. And of course, APC, angled physical contact. The faces are angled even tighter in a connection to and better return loss performance. APC cannot be mixed with PC or UPC. These connectors are usually deployed when the fiber is being used to carry analoging signal, as in cable access TV, CCTV, CATV networks. They are also increasingly used for long-distance transmission and for passive optical networks, PON, such as those used to implement fiber to the XFTTX multiple subscriber networks. It is important to match the finishing type when you are selecting a connector type. APC finishing is not supported by patch panels, transceivers, and switch ports designed for Ethernet. So remember, if you're going to terminate with APC, you won't be able to get that into a switch or have that spit out Ethernet. Okay, where there are multiple strands within a single cable, the strands are color-coded as per the guidance of TIA EIA 598 to differentiate them. Also by convention, cable jackets and connectors use the following color coding. And those aren't here for you guys, so this is another instance. I'm going to take a screenshot. It's in the book for you, but that way you guys can also OneNote it and have a quick reference. I'm going to pull it up over here. OM1, jacket color orange, connector color beige. OM2, orange, black. OM3 and 4 are both aqua. SMF, PC, UPC, yellow and blue. SMF, APC, yellow and green. And remember, APC cannot be used with PC and UPC. So now that we're done with fiber optic, we'll move on to a little bit of review for us. So let's get our fingers ready to type.
In this video, we'd like to take a look at a couple of the different types of fiber optic patch cords and the modules that they will be attached to in this video. Let's go ahead and get started. Now here you will see that I actually got a couple of cables. These cables here are our fiber optic cables, and we've got a couple different kinds here. We've actually got an older one that you might find in your networks, because this has on one side, it has what's known as the subscriber connector, or SC connector, subscriber connector, standard connector. And then on the other side, you can see about half the form factor here, half the size really, is what's known as the more modern LC connector, the Lucian connector or local connector. And this is good when you had older standards that, or older devices, switches if you will, that needed to connect to newer switches. So this would allow you some of that interoperability when you had two dissimilar fiber optic cables or connectors that you needed to implement. Now, that one being said here, we also have another type of cable here as well, and this is actually our Lucian cable, LC cable. It's got both the LC connector on one side and the LC connector on both sides, and when you look at them, you can see that they are, for the most part, they're not really much different. You can see that this one's a little bit thinner than this one is here, and you can also see, if you compare the two connectors here, that we have our LC connector here, and this one happens to have the caps over the fiber, the core there as well. I've gone ahead and I've removed the fiber or the caps here from the fiber core here, so you can see this. And these are what go inside of our devices within our server closets. Now, the next thing that we have right next to this is what we connect to. These are SFPs. The small form factor pluggable modules. SFP Plus is also a form factor here. And what we can see is that this is actually the 10 base SR, so that's the short range, if you will, one of the most common of the 10G base, excuse me, 10 gig network. So 10G, one of the most popular fiber connectors, and this is one that runs shorter distances than the single mode fiber, which runs much longer. This is a multi-mode cable that has a distance of 300 meters, and you can actually see this right here on the package, that it's also 850 nanometer wavelength. And they also have them labeled here on top of your little modules here. A little hard to see, but the great thing is we can see the labeling here in the package too, so if you can't see that, this is what we're looking at, and it does tell us the standard. It tells us that it's 10G network, it's 850 nanometers, that it is multi-mode, and then it goes 300 meters length. So remember, multi-mode fiber, shorter length than the single mode fiber. Now, if we want to see what the connections of these cables look like, let's go ahead and I'll take our first module here, and there's a little faceplate on it that you need to, or a little latch that you got to pull down so that you can connect these, and we'll go ahead and we'll connect this one, and it's got a latching lock, much like the Ethernet RJ45 jack does, and this is locked in, and again, it would be slipped into the switch. We'll go ahead and take the fiber core protectors here off. We'll take the caps off of here, and here you'll see that little lever a little bit easier there. We pull that lever down, and then latching lock mechanism here, we'll go ahead and we'll put these in, and you'll hear it click. And this is a fairly furrow connector here, and that's what you need here for, especially for your fiber optics cabling, again, because, well, the fiber optic core is very, very delicate. And then in the end, what it ends up looking like, you will see, is that the cables all come down in your premise wiring, and they connect to the front of the switch there, and that's how you make those connections, and an example of some of the fiber optic patch cords that you could potentially see within your networks.
Now that we're done with fiber optic, we'll move on to a little bit of review for us. So let's get our fingers ready to type.